we're going to do a little comparison. I'm going to draw three different people here, or it could be the same person, I suppose, in three different situations. So you've got the first person just kind of sitting, and maybe they're watching a YouTube video on their laptop. And you've got a second person who's actually going for a little walk. Let's see if I can draw this person walking. And you've got a third person who's, let's say this person is actually really active, and they are running. So they're actually in full stride running, and maybe they're late for a test or something. So, let me actually change that so their arm does not look broken. So that you have these three people, and they're running and walking and sitting, right? So you can imagine if you were to kind of take a look at their heart cells, they might be doing different things. In fact, let's draw all three's heart cells and show you what they might be doing. So we've got our heart cell, and in this case, I'm actually going to draw also a nerve. This is going to be the sympathetic nerve. I'll write an S for sympathetic nerve. And the heart cell, just to be clear, is going to be a ventricular heart cell. So this is I'll write ventricular heart cell here, just so that we know we're not talking about some pacemaker cell or some other cell in the heart. This is a ventricular cell. And now just to kind of remind us of a couple things we know, this ventricular cell is branched, and it's got two little nuclei, and it's got some receptors on its surface waiting for potentially norepinephrine from that sympathetic nerve, right? Now, inside of that heart cell, if we were to dive inside of the heart cell, you might see some actin, and you'd see that at the ends of the actin, it's a Z disc, right? So we've got a Z disc with our actin, and I've drawn this far too close together. Let me actually make a little bit of space in here. But you get the idea. You've got our actin kind of like little ropes, and in the middle you've got our myosin. And our myosin, you remember, is basically going to have a whole bunch of myosin heads, and these heads are going to want to do work. They're going to want to kind of pull the actin and yank that Z disc closer to the middle, right? That's what they want to do. So these myosins are kind of hanging here waiting to do work, and their trigger for work, of course, is going to be calcium binding the troponin C and pulling tropomyosin out of the way. So this is our actin and myosin. This is our actin up here, actin, and we've got our myosin in the middle. And then finally, I'll draw one last thing, and that is the titin. And the titin, remember, is a protein that basically is going to attach the myosin to the Z disc. Remember, our Z disc is this thing at the end. This is our Z disc over here. Let me just kind of draw it in for us. This right here is our Z disc. And I've been calling it Z disc. Sometimes you see Z line. It's kind of interchangeable. But this is our Z disc right here. And it's basically tethered by those actin ropes, you can think of them as. And we're going to use those ropes to pull the Z discs together, right? So this is basically kind of the setup and what it looks like. And now I'm actually going to just take this and cut and paste it a couple of times so that we can actually use this for our two other situations, right? We've got one there, and we can actually do it again and have it like so. So now you can see our three situations kind of side by side, and our three setups with our actin, myosin, and our Z discs. So what would happen in situation one? Well, in situation one, you're just kind of hanging out, you're happy, you're maybe watching something kind of funny on YouTube, and you don't have much sympathetic drive, right? You don't have any stimulation coming from your sympathetic nerves. You're not running, or you're not frightened, let's say. So you have, your normal amount of calcium comes into this cell when it's time to contract, and so you get a little bit of calcium in here. And when the calcium, kind of looking over at the other side, when the calcium comes in, you have a low amount of calcium, let's say, because not much is coming through the channel. You're not activating that channel in any way. So that calcium, let's say it binds here, and it binds here, and let's say a little calcium binds here and here. And when I say binds, remember, I mean it binds the troponin C. Remember that. So the calcium binds there, and what do you get? Well, let's draw a little table on the side of this. Is, let's say, the proportion, I'm trying to make sure I phrase it correctly, the proportion of myosin heads that are working. So the proportion of myosin heads that are working. And if you count them up, if you count up all the little purple heads, you can do that right now, you'll see there are 20. So this is the proportion of myosin heads that are working. And what would you get for this first situation? Well, at 4 spots, the calcium has bound, right? And it doesn't bind forever. At some point, the calcium is going to be kind of taken back into the sarcoplasmic reticulum or thrown out of the cell. But for the time that our heart is contracting, for that brief bit of time, how many myosin heads are working? Well, we've got this guy over here, this guy, and we've got this guy down here, and we've got this guy and this guy. So 4 of them are working. And that means that 16 are not working, right? So 4 out of 20 are working. So really we've got, what does that work out to? 20%, right? That's equal to 20% of them are working. So that's not too many. But what's going to happen? Basically, these myosin heads are going to pull. Let me erase the little arrows not to confuse you. But basically, these myosin heads, these 4 that are working, are going to pull the actin that way, and this way, and this way. And the Z discs will come closer together. Let's not be confused about that point. The Z discs definitely will come together, but it's going to take a while. I mean, it's going to be, really, it's like having 4, you could think of it as 4 of your friends pulling on a rope. It's not as effective as having 20, right? So let's go to situation number 2. So in situation number 2, you're let's say now you're going for a walk, and you're enjoying the beautiful day. But you're walking, right? And so there's a little bit of activity. And so let's say your sympathetics are firing a little bit of a sympathetic drive here. And a little bit of neurotransmitter gets released. And so this neurotransmitter we know is called norepinephrine. So a little bit gets released into that space between the nerve and the cell, the heart cell. And it binds to, let's say, one of the receptors. So one of the receptors is going to fire, and during a muscle contraction you've got calcium coming in, but because that receptor fired, now you have a little bit extra calcium coming in, meaning that channel has been activated so that it's letting more calcium in. Okay, so if more calcium's coming in, let's now take a look at our diagram. Now you've got a little bit more calcium coming in and binding, and let's say, and I'm just kind of choosing them by random in a sense, but let's say these 6. And on this side, let's just choose another 6. Let's say 4 up here and maybe a couple down here are going to bind calcium. So you've got troponin Cs that are binding calcium. And of course, that means that those are the myosin heads that get to work. And so in total, how many myosin heads are working? Well, now instead of only 4 total, we've got, 12 myosin heads out of 20 working, or 60%. So it's really gone up considerably. So just as before, you're going to have the Z discs getting yanked in, but now the yanking is going to be much more forceful because you've got many more myosin heads actually involved in dragging that Z disc over. So this is actually quite interesting because now you can see that you have, as a result of the sympathetic drive, more force in your contraction, your heart contraction. So you can probably guess where the last one is going to go. It's now you're running, you're excited, and let's say now instead of just a little bit of transmitter, you've got tons of neurotransmitter being released, lots and lots of norepinephrine. In fact, let's say a little bit over here, and you've got all 3 receptors kind of firing, right? Because all that norepinephrine is allowing lots and lots of stimulation to the cell. And so with all this norepinephrine, your calcium channels are going to be really active, right? They're going to be pouring in calcium. So instead of just a little bit of calcium, now when you have a contraction, you've got lots of calcium dumping into the cell, right? And this is, of course, just during the time when you're contracting or squeezing. So with all this calcium now, it's going to go and bind the troponin C everywhere it can find a troponin C. It's going to come and sit basically everywhere. And all these myosin heads are excited because now they all get to work. And with this full kind of set of myosin heads working. You have 20 out of 20 working. You have 100% of them doing their job. And as a result, you can see that now you're going to have a huge mechanical force, enormous forces, yanking those Z disks closer together. So in all three situations, you do get the Z disks coming together. But remember, the period of time that the calcium is in the heart is finite, right? I mean, it's not like it's there forever, because at some point that calcium is going to get, as we said, brought back out of the cell or into the sarcoplasmic reticulum. So while it's there for those few precious moments that the calcium is there, you really want your heart to be able to do as much work as possible. And in this case, you're actually seeing that here at the top. Let's actually draw an arrow. At the top, this side, there's really low energy use because not too many of the myosin heads are actually converting ATP to ADP plus phosphate. So remember, the myosin heads that are working, those are the only ones that are actually converting ATP to ADP plus phosphate. And the ones that are not working are, of course, not doing that. So in this case, you can also see that in addition to force, the other thing that's less in this sitting situation is that it's a low energy state. You're not really burning any energy. Whereas over here, when you're running, each one of these myosin heads is cranking through ATP. It's making lots and lots of ADP. So it's using lots of energy. It's a high energy situation. In other words, you're using up a lot of energy here. And so, of course, this makes sense, right? Because you think, well, if I go for a run, of course I'm going to use up, energy. Whereas if I'm just sitting, I'm not using much energy at all. And now you can see exactly why that's the case. Because in the running situation, all 20 of your myosin heads are burning through ATP.